Right, so question. Who here has used NumPy or SciPy either to multiply matrices? Oh, amazing. It's about half the people here. Much more than I thought. Because my second question is, who here has either seen or tasted a pineapple? Right, so you are all in the right place. That's not a pineapple. That's a really, really big thing. It's the closest big thing I could think of. Well, it's certainly the closest big thing to here that I can remember. So that's why it's there, because it's big. And it's a pineapple. Okay, so this talk is really about a particular application in bioinformatics. It's an application in bioinformatics where you are comparing two biological sequences, and for example, I'm going to say they're DNA sequences, but you could actually compare proteins and use the same sort of mathematical structure. But the idea is that there's two ways of comparing biological sequences. One is what we heard about this morning, which is by aligning the sequences, splitting up each of the sequences into bits and aligning them. And another is by statistics, a statistical comparison of two sequences using features of the sequences. And so it's the second one that I'm going to talk about. There is a particular statistic on pairs of sequences called the D2 statistic. I should have mentioned from the previous slide, this is joint work with Sylvain Faure and Conrad Burden at ANU. And in fact, it stems from an ARC grant, which was also with Sue Wilson, having to do with analysing the properties of this D2 statistic under certain assumptions, which I won't go into here because they're not relevant to this talk. But the main point from this slide, sorry for too many words, is that this D2 statistic is just the inner product of two vectors. So it's just very simple from that point of view. So why do I say that? So, here we go. We have two biological sequences, A and B. And so we're trying to define this thing called a D2 statistic. All it is you take a fixed word size and you move that word size along each of the two sequences and you get words of that length. So here we have a word size K, and K is 7. You move that little window of length 7 along the sequence to get each of the words. And what you do is you say, okay, I've got this particular word, say ATGCTTT. And what you want to do is count how many matches there are between the two sequences. So in this particular case, there are two matches. The first one being from that word occurring on the left-hand side of the A, and the one instance on the B, and the second match being this one up here, where it's almost up to the end and matching the first B. So we've got two matches for that word, one match for the other, A, G, C, it's like an eye test, isn't it? Whatever that is. So we've got a total of 3 matches. So that's one way you can figure out what this D2 statistic is, which sounds very daft. But in fact, if you think about it for a little while, you can see what you're actually doing is you're creating histograms. So each of the two sequences, you go through and you count the number of occurrences of each of the possible words of that length. And then you just take the inner product between the two, and that'll give you the right number. And really, apologies for too much mathematics and too many words. But anyway, what I wanted to explain from this is that you have this idea of you go through each pair of sequences, and you create this count vector for each sequence, and pairwise you just get inner products. So then you really have now a two-step process. And the two steps are, first step is for each biological sequence that you start with, you create a count vector of the word counts for that particular fixed size corresponding to that sequence. And then the second step is pairwise you do inner products. So then you can think of having a database with queries. So your database contains the word count vectors corresponding to the biological sequences that you know about, and your query has to do with the sequences you want to find out about, and you just create the word count vectors for that. And then what you wind up with is essentially a sequence of inner products between the vectors you want to find out about and the vectors you already know. Well, guess what that is? It's a matrix multiplication. But it's a matrix multiplication where we have one particular problem. And that's the one particular problem and the one particular fix. So the matrix multiplication has a particular problem. And the particular problem is that sometimes biologists are interested in large K. And if K gets particularly large, and you're dealing with DNA sequences, 4 to the K gets very, very large. And if you have something that's that big, then you don't want to have full vectors. You want to have sparse ones. And that means that your matrices will become sparse. Fine. But even so, if you've got a database which is large enough, you want to have, for example, a column for each of the sequences that you have converted into a count vector. Well, maybe the number of columns is millions, maybe it's billions. It depends on what it is your application is. So it's quite possible that if you're using a tiny little laptop like what I've got, that your database, even if it's represented as a sparse matrix, may not fit into memory. So that's the issue. And possibly should have split this into 2 slides. That's the issue. The slide is talking about the solution. Okay, so who here has used SciPy sparse matrices? A few. Certainly less than know what a pineapple is. So there's this idea of sparse matrices and sparse matrix multiplication. A lot of that is actually built into SciPy. And there's some complications involved, really. Building the sparse matrix, figuring out what type of sparse matrices is more than one of them, building them, and then multiplying. Well, multiplying them actually is fairly straightforward. It's building and figuring out that's the hard part. Okay, so who here has used NumPy memmap? Very, very small number of people. How have you found the use of NumPy memmap? So it wasn't actually... So just out of curiosity, not actually an application. And sorry, the guy behind? Out of curiosity. Right, so I'm definitely in the wrong room. I should just sit down and shut up. No, okay, so the idea is you've got something that's too big to fit into memory. Well, what can you do? Well, one thing you can do for some array that's too big to fit into memory is to use this thing called a NumPy memmap. And the idea of that is that you hive off what's supposed to be in memory to disk somewhere, and NumPy magically does something that allows you to access it. And luckily, there's enough documentation in memmap to be able to sort of make sense of that process. I mean, when you took a look at the documentation from memmap, did any of it make any sense? Okay, so what I wound up doing in this particular application was a combination of the two things. And that is to split the matrix multiplication up into, I've got this database which has got a lot of columns. I'm going to split the database up into slices by column. And then the slices are the things that I'm actually going to be referencing via the NumPy memmaps. And that's what the dot points at the bottom have to do with, is that there's some classes that I need to set up and two processes, well, two functions that I need to create. One is the one that creates the memmaps, and the other one is the one that uses the memmaps to do the multiplication. So this is what this talk is about. It's all about slices and memmaps and slices. So those people who've fallen asleep so far, that is a pineapple. Well, that's what's left of a pineapple after you've sliced it a bit. What's that, sorry?
The comment at the bottom was so geeky.
Oh, yes, this image is a work of the United States Department of Health and Human Services taken or made as part of that person's official duties. As a work of the US federal government, this image is in the public domain. I've got attributions for all of my images to make sure that I'm kosher as far as, yes. So first piece of code. And, right, so code. There's a class that defines the end of a slice, not so interesting. There's a class that basically defines what I mean by the memmaps, three of them, that I'm going to use for a sparse matrix. So what happens is that when you assemble a sparse matrix, you need data to assemble into a sparse matrix. And that data is the data, the rows, and the column indices that go into building the sparse matrix. Well, if the sparse matrix is ginormous, then guess what? All of them are going to be memmaps. So all of this class does is just encapsulates the information you need for further memmaps. And has a nice sort of wrap up at the end when you do the delete to get rid of the files and the directories you need. So that's the thing, you know, you're storing memmaps, and therefore you need to actually deal with the file structure on the machine. Okay, first fairly horrible routine. What you want to do is, when you're building this, these memmaps, you're taking one count vector at a time to build your database of biological sequences. What you do is firstly set up here. Well, there's a typo there. That should be Python with an H. This is coded in Python, by the way, rather than Python. So this is why you've got these cdef ints and some strange syntax there. But most of the rest of the syntax is actually Python syntax and pretty much the same. But here's the guts. You actually have to explicitly call something which sets up memmaps and gives the file names and has to deal with a whole bunch of junk, basically. But you do that. You set up the memmaps. And then, if scrolling thingy works, yes, good. And then once you've set it up the files for the memmaps, you have a nice loop which assembles it by slice. If I can get to the beginning of the loop. Yeah. Okay. That's all we do. We assemble these memmaps by slice. So append to our list, track the number of non-zeros. But the first thing is assemble the count vectors, columns of a sparse matrix. So the first thing is that this thing called gen DNA frequency, all that is just get the next vector that I'm going to put into a column of my database. Then keep track of some lists, track the number of non-zeros. You have sparse matrices, that's what you need to do, is keep track of the number of non-zeros to make sure you know how big it is. And also each of these different data rows and cols are indexed by the number of non-zeros. You keep track of the columns. You keep track, in this particular case, the added structure I've got is these slices. And you append the data to the mem maps. And that's it. When we reach the last slice, we append some information about where the end of the slice is. As we go through, we keep track of where the ends of the slices are. Right at the end, we create a tuple that corresponds to our shape, and then we do the usual call. Well, no, we don't. Not at this point. At this point, all we do is we create one of these memmap classes, which just takes our data that we've got so far, which is the data, the rows, the cols, the shape, and the ends list. And that's it. So all we've done so far is just taken each of the individual vectors and pulled them into our three mem maps. And that's the database part. We haven't got to the query part yet. So here's the query part. Our query part looks suspiciously, and try saying that after lunch, and I didn't have a beer, by the way. It looks like a matrix multiplication. Well, the first part does. You know, there's a try except, and in the first part of that try, all I'm doing is just a matrix multiplication and making sure that I have a dense result, because I'm assuming that the result can be dense and the result will fit in memory. So that part is easy. So that means if my right-hand side is just a matrix, I have a matrix multiplication. And I assume that if it doesn't work and it bombs out, that if it bombs out because of a value error, then it's because I have my new class that has these NumPy mem maps at the back of it. And all this rest of the routine, setting up some local variables, etc., is just the matrix multiplication. And that matrix multiplication uses those slices. So it says perform the matrix multiplication by column slices of the right-hand side. So it just goes through this list of slices, which is the thing that I stored in the class, and picks up the slices from the mem map. So you've got data, rows, cols, pulls out that particular part of the slice having to do with the data, the rows and the cols into those local variables, and then figures out what the shape is and creates, and I'll scroll that up so you can see it. Yeah. And then creates a SciPy sparse matrix using this shape and just the CSR matrix call in SciPy sparse. So it creates the sparse matrix. So the sparse matrix is just a sparse matrix corresponding to a slice and not the whole thing. Does the matrix multiplication. Your matrix multiplication is just for that slice and just goes around in a loop. So the idea is to be able to do that with a reasonable amount of memory on a single processor machine with a vast database. You may say, well, you know, what's the point? Well, there are alternatives. One alternative is to do it with MPI. If you do it with MPI, you need to have, well, for it to make sense, you need to have a cluster. That way, you know, you can use your cluster to maximum advantage. But if you've only got a laptop, this is one way of doing that big matrix multiplication task. a version of the code is up on GitHub. Not this version of the code because I was just chomping on it at lunchtime and I haven't put it up yet. Yeah, I'm not going to read out that blurb at the bottom, but basically that's our pineapple under construction. And that's it for the moment.
But thank you very much, Paul. Do we have any questions? Yes,
Yeah.
1, 2.
Does it come with free snake line?
Yep.
Thank you. Just a few questions. Firstly, I'm assuming you're just doing KME accounting. Have you got any comments about how fast your code is? Because normally if I'm doing KME accounting, I want it to be fast.
It is usably quick for the sort of prototyping work I'm currently doing.
Have you compared this to other KME accounting libraries?
No.
Okay,
No,
cool.
I haven't. The point is that I want to be able to do this particular inner product. It's the inner product itself that matters rather than the KME accounts. The thing is that I have seen at least some of the KME account libraries that are available via Python, and I can use them. And in fact, one of the things that I didn't show you is some of the rest of the code. It pulls up BioPython and uses that, especially for faster file reading. If you know anything about that.
So the other question, I'm assuming the memory is a big problem. Have you looked at using like a Bloom filter? I'm assuming.
What, sorry?
Is it a Bloom filter? People normally use a Bloom filter algorithm to sort of get around this memory issue.
I don't know what that is. I'll have to talk to you about it later.
Okay, cool. Thank you.
There's one other question. Oh, yes.
Yeah.
Is there a strong reason why your class couldn't match the interface of scipy.sparse directly so that would just work when you do a dot product using the scipy.sparse library?
Only because I threw it together rather quickly and hadn't really thought very well about what the interface should look like.
Okay.
I
I'm
mean,
not sure. There could be strong reasons why it doesn't work, but maybe it would, and that would be exciting.
Well, yeah. I mean, it would be nice anyway if there was an extension to sparse matrices that did all of this sort of all of this sort of memmap stuff in the background. But I was just thinking that if there was, then maybe it shouldn't be coded in Python or even in Python. It should be, back somewhere inside SciPy.
Yeah, I was just wondering, so you're saying that you can actually get reasonable performance about this, and you can actually run that on your local machine?
Yeah,
there?
it runs on a laptop with reasonable sized databases. But I mean, I haven't done a lot of timing on it. I've only put the code together quite recently.
Sure, fair enough. So have you tried it on something like a larger machine? Does that get any appreciable performance increase?
I can't answer that question very well. The one point that I can make, though, is that if you have a large enough machine, you're probably better off trying to use MPI, especially if you've got a cluster. Then the main problem that you're trying to get rid of here is alleviated simply by the fact that you've got multiple machines, and each of which has enough memory to be able to do the job. So piling all those machines together means you can take your database and split it up across the machines, and that gets rid of the issue altogether.
I have a question too.
Yeah.
And that's whether you'd be willing to contribute your coda to scipy.sparse. It might belong there it might fit there quite nicely.
I would, but I think it needs a lot of work done. Basically, it needs to be, as you suggested, refactored to get the interface right. But also there needs to be a bunch of instrumentation done on timing and otherwise to make sure that it's actually working properly. I mean, one of the issues I had was really just seeing what the performance of MEMMAP actually is for this sort of task, and maybe MEMMAP wasn't written for this sort of an application. So, and I don't know enough about the guts of MEMMAP to be able to go in and instrument it. So, talk to me about it later, and we'll try and figure out how that should work.
Terrific. Okay, well, thanks again.